In geometry and science, a cross-section is the intersection of a body in three-dimensional space with a plane, or the analog in higher dimensional space. Cutting an object into slices creates many parallel cross-sections. A cross-section of three-dimensional space that is parallel to two of the axes is a contour line. For example, if a plane cuts through mountains of a raised relief map parallel to the ground, the result is a contour line in two-dimensional space showing points of equal altitude. Conic sections. Conic sections, circles, ellipses, parabolas, and hyperbolas, are formed by cross-sections of a cone at various different angles, as seen in the diagram at left. Any planar cross-section passing through the center of an ellipsoid forms an ellipse on its surface, which degenerates to a circle for sections perpendicular to a symmetry axis. A cross-section of a cylinder is a circle if the cross-section is parallel to the cylinder's base, or an ellipse with non-zero eccentricity if it is neither parallel nor perpendicular to the base. If the cross-section is perpendicular to the base, it consists of two parallel line segments unless it is just tangent to the cylinder, in which case it is a single line segment. Other mathematical examples. A cross-section of a polyhedron is a polygon. A cross-section of a probability density function of two random variables in which the cross-sectioning plane is at a fixed value of one of the variables is a conditional density function of the other variable. If instead the cross-section is taken for a fixed value of the density, the result is an isodensity contour. For the normal distribution, these contours are ellipses. A cross-section can be used to visualize the partial derivative of a function with respect to one of its arguments, as shown at left. Suppose z equals f. In taking the partial derivative of f with respect to x, one can take a cross-section of the function f at a fixed value of y to plot z solely against x. Then the partial derivative with respect to x is the slope of the resulting two-dimensional graph. In economics, a production function f specifies the output that can be produced by various quantities x and y of inputs, typically labor and physical capital. The production function of a firm or a society can be plotted in three-dimensional space. If a cross-section is taken parallel to the x-y plane, the result is an isoquant showing the various combinations of labor and capital usage that would result in the level of output given by the height of the cross-section. Alternatively, if a cross-section of the production function is taken at a fixed level of y that is parallel to the x, z plane, then the result is a two-dimensional graph showing how much output can be produced at each of various values of usage x of one input, combined with the fixed value of the other input y. Also in economics, a cardinal or ordinal utility function U gives the degree of satisfaction of a consumer obtained by consuming quantities W and V of two goods. If a cross-section of the utility function is taken at a given height, the two-dimensional result is an indifference curve showing various alternative combinations of consumed amounts W and V of the two goods, all of which give the specified level of utility. Examples in science. In geology, the structure of the interior of a planet is often illustrated using a diagram of a cross-section of the planet that passes through the planet's center, as in the cross-section of Earth at right. Cross-sections are often used in anatomy to illustrate the inner structure of an organ, as shown at left. A cross-section of a tree trunk, as shown at left, reveals growth rings that can be used to find the age of the tree and the temporal properties of its environment, area and volume. Cavalaris' principle states that solids with corresponding cross-sections of equal areas have equal volumes. The cross-sectional area by taking the absolute value of the integrand and dividing by 2. Cross-section of four-dimensional space. If a four-dimensional object passed through our three-dimensional space, we would see a three-dimensional cross-section of the four-dimensional object, such as a sphere that increased and then decreased in apparent size during the encounter.